For our feedback control project, we have chosen to construct a classical inverted pendulum that consists of a long rod mounted on low friction bearings sitting on a movable cart. Due to the instability of the pendulum, the rod would immediately fall to one side without action control. The cart beneath the pendulum will be programmed to move in a corrective action in order to keep the rod upright for as long as possible. A sensor will identify the angle of the inverted pendulum, and a controller will attempt to keep it in the upright position. Or, as Thanos once said,
"Look. Pretty, isn't it? Perfectly balanced, as all things should be."
For the pendulum and the cart system, the equations of motions were derived using Lagrangian technique. We realized that the system had 2 degrees of freedom, the angular rotation of the pendulum and the translation of the cart, and this gives us 2 equations of motions that you can see in the matrix form below. The block diagram highlights the different processes which build up our pendulum system. The angle measured by the sensor will be reported back to the controller, which provides the required voltage to the motor. Voltage that can provide enough torque to the wheels to compensate for angle change. The last block on the diagram describes the simplified equation of motion for the pendulum in the Laplace domain. We derived the overall transfer function equation from the block diagram, which would further help us analyze the system stability. We used Routh-Horowitz technique to analyze the stability. After a failed couple of trials, one with no controller gain or the one with just the P controller, we realized that a PD controller can help us ensure the system stability. The ranges for the proportional and derivative controller gains can be seen here.
Here is our 3D CAD model for our intended pendulum design. It consists of a 3D printed body, 4 axial wheels, and 1 inverted pendulum mounted on 2 bearings. We 3D printed our body of the cart using the UGA MakerBots. Our team took a trip to Home Depot to acquire parts for the upright pendulum. We used an aluminum bar as the actual pendulum, 1/4-inch bearings to reduce friction, and an aluminum crossbar. We also 3D printed some stylish wheels to add to the design. The bearing assembly makes the inverted pendulum frictionless, meaning that it will fall to either side when released from the vertical position.
The first Arduino we used was the Mega 2560R3, but due to an unexpected short circuit, we destroyed that Arduino, forcing us to use the Arduino Uno R3. The sensor we decided to use was the GY521 gyroscope accelerometer, which measures the linear acceleration in the 3-axis position and angular velocity. The first motor driver we decided to use was the L293D, but we soon learned that it could not provide enough current to our motors, so we decided to change to the L298, which provided more than enough current for our system. The motor driver connects directly to a 9-volt DC gear motor, which delivers torque directly to the axle of our wheels to drive our cart. Here you can see the wiring diagram for our inverted pendulum system, where our gyroscope connects to the Arduino, and the Arduino is connected to the motor driver, and how our motor connects to our motor driver. And then now you can see in reality the wiring system. This is the Arduino code for our inverted pendulum system. We started out defining the pins of the motor driver and initializing the variables for the error, proportional, and derivative gains. For the setup of the code, we calculated the offsets of the gyroscope to assure accuracy of the measured angles. We also defined the output pins on the Arduino for the motor driver. Then, for the actual feedback control part of the code, we measured the angular displacement of the pendulum and compared that to our reference angle of 0 degrees in the vertical direction. Using that error, we determined the corrective action by adjusting the error with our proportional and derivative controller gains. The corrective action is then sent as a voltage to the motor driver to turn the motor either counterclockwise or clockwise based on the sign of the error. However, if the measured angle and the reference angle are the same, meaning the error is 0, then the output voltage is 0 for our motor driver.
Shown here is the open loop system of our project because the car is not actually moving to create a corrective action. For visual demonstration, we have replaced the motors with LED lights. As you can see, they become brighter or dimmer based on the magnitude of the angular displacement from the vertical reference point. Also, the lights changing colors represents the motor's changing direction. Despite the wiring and mounted sensor, the pendulum still remains frictionless and falls when released. Now we have completed our assembly and attached the wheels. A wooden plank was also introduced to provide more space for components. The wheels turn to create a corrective action for the pendulum deviation when the weight of the cart is not completely applied to the motor. However, when the cart is placed on the floor and the full weight of the system is applied to the motor does not provide enough torque to overcome the friction and supply the corrective action necessary to keep the system stable for more than a second or two. Here I am moving the inverted pendulum in small increments. You can see that the motor is reacting in time, it's just not providing enough power to keep the pendulum upright.